Hello, today I'm going to be talking about this article called Comparative Circadian Metabolomics, and it's published by the Journal of Biological Chemistry. So, using metabolomics to analyze metabolites, 362 known metabolites, as you can see in Figure A, were found in the serum. 33.6% of these were not present in the liver, however. In both tissues, 62% of the metabolites in the serum and 77% of the metabolites in the liver were affected by the high fat density diet. The oscillation of metabolites in the serum and liver were kept steady, however, with a change in diet, as you can see in Figure B. 46% of the metabolites in both oscillated with either normal condition or with the high fat density diet. Figure C showed the amount of metabolites that oscillated in the serum and the liver in the normal condition, the high fat density condition, and both diets, respectively. There was a threefold decrease in the number of oscillating metabolites in the high fat density diet in the serum relative to the normal condition. This shows that the serum metabolome is much more sensitive to nutritional challenge than the liver. Figure D and E show that the serum metabolites in the high fat density condition were much more phase advanced than in the normal condition. Liver metabolites were somewhat more phase advanced in the high fat density than in the normal condition diet, as well as seen in Figure E. IL-6, adiponectin, and leptin levels were analyzed at two different time points in both the normal condition and the high fat density mice to see whether the obese status given at ZT16 affected circadian secretion of these adipokines. Figures A and B show that there was no significant difference between the IL-6 and the adiponectin in either the normal condition or the high fat density condition mice in either the serum or the liver. Figure C, though, shows that leptin levels increased dramatically in the high fat density diet when compared to the normal condition in both the serum and the liver. To extend the analysis, researchers monitored the AKY, or the AKT, as well as the GSK3 beta, to find that the high fat density diet induced increased basal AKT phosphorylation and inactivation of the GSK3 beta. Figure A shows that the amount of oscillating metabolites in the serum, liver, and both were around the same. There were only 8 metabolites oscillating in both tissues under the normal condition, and they all showed a similar phase peak as seen in Figure D. In Figure C, you can see the names of all of these metabolites that were shared, and in B, you can see there were only 8. Sorry, 1 second. Figure E shows, however, that 75.5% of the serum lipids oscillated in the normal condition versus 36% of liver lipids in the normal condition. 18% of the shared nucleotide metabolites oscillated in the liver, but none in the serum. Figure F shows that only 2 metabolites were shared between the liver and the serum. And Figure G shows that 52% of the liver lipid metabolites cycled and only 33% of serum lipid metabolites cycled during the high fat density diet. Figure H shows the names of the 14 metabolites that are shared and oscillate under both of the feeding conditions in both of the tissues. Unlike the liver, however, serum metabolome is not phase advanced under the high fat density diet like it is in the liver. Amino acids were also measured. A significant amount of amino acid metabolites are shared by both serum and liver, but 40% of all of the amino acid metabolites were found in the serum, as you can see in Figure A. Figure C shows that fewer amino acids oscillated in the serum than in the liver, and Figure D shows that there was a twofold reduction in amino acid metabolites affected by the high fat density diet in the serum as compared to the liver, which again shows that the serum is more susceptible to nutritional challenge, such as the high fat density diet. Some metabolites in the liver completely lost oscillation in the high fat density diet, HFD, while others only showed oscillation under HFD in the serum, as you can see in Figure E. I know it's hard to read. Figure F showed that most of the metabolites in the serum and liver peaked at the time ZT16 under normal condition and ZT20 under high-fat diet. Peptide metabolites were analyzed as well. Figures A and B showed the peptide metabolite composition in serum and liver. Very few peptide metabolites were found in the liver. In the serum, though, 58% of the metabolites oscillated, and in the liver, 43% of them did, as you can see in Figure C. Figure D shows an increase in circulating peptides in the serum compared with liver in the high-fat density diet and the loss of circulating peptides in serum compared with liver in the normal condition. Nucleotides are also measured. Adenine and guanine levels were significantly different in the liver and the serum. Adenine was shown to be more in the serum and guanine more in the liver. In particular, though, no oscillating nucleotides were found under normal conditions in the serum. Nucleotide metabolites peaked as ZT4 in the serum under both normal condition and high-fat density diet. In the liver, however, the nucleotides were phase advanced under the high-fat density diet. Carbohydrates are measured and found to be either in both organs or the liver. The serum had very few exclusive carbohydrate metabolites, as seen in figures A and B, as you can see with the black. Figure C showed that only 4 metabolites circled in the serum under normal condition and 20 did in the liver under normal condition. The cycling of carbs appeared to be more prominent in the liver, as seen in figures D, E, and F, which is a site of glucose production and uptake. Serum doesn't play a big role in glucose manufacturing, which is why there weren't that many metabolites seen. 33% of the lipid metabolites found were not in the liver, but only in the serum. Figure A2 shows that 55% of the serum metabolites oscillated, but only 33.3% of liver metabolites oscillated. Specifically, higher liver lipid metabolites oscillated than serum ones under normal conditions. Only 28% of the liver metabolites showed change to high-fat density diet, and most of the serum lipid metabolites showed a reduction in oscillation, as you can see in figure C. Also hard to read. Figures D and E show that serum in the high-fat density diet were phase reduced in comparison to the normal condition, and liver lipid metabolites stayed unchanged. Cofactor comparison showed the absence of vitamin B5, folate, and thiamine metabolites in the serum, yet present in the liver. 91% of the serum metabolites never circled, and the remaining 9% circled only under normal conditions, as you can see in figure D. 57% of liver metabolites for cofactors oscillated. Figures F and G show that for xenobiotics, 41%, that for xenobiotics, 41% of serum oscillated. Serum metabolites oscillated, and 27% of the liver metabolites oscillated. Under the high-fat density diet, all liver oscillation was lost, as you can see in H and I. Figure E shows that the serum metabolites are phase advanced under normal condition compared to the liver under normal condition. Figures K and N, K, M, and N show that the energy metabolites remained unchanged in both normal condition and the high-fat density diet condition, suggesting that these are critical for survival and remain constant, even under nutritional challenge like the high-fat density diet. A, B, C, D, E, all the way to the right here, just summarize all of the serum metabolites affected by the high-fat density diet. So in summary, the study analyzed the changes in serum metabolites and the circadian cycle as compared to the liver with changes in diet. It is seen that the serum is devoid of oscillation after a high-fat density diet, and the remaining cycling is not in sync with the liver clock, showing a disconnect from the SCN, which controls the rest of the body's circadian rhythm. Increased abundance of non-circling lysolipids under the high-fat density diet reflect breakdown in muscle and adipose tissue. These are risk factors for obesity. Fatty acid, cresol sulfate, inosine, and daidzein metabolite changes in the serum also showed risk factors for cardiovascular disease and renal failure. Some of the metabolites found in the serum under high-fat density diet are also linked to cancer. Overall, nutritional challenge from a high-fat diet is shown to disrupt the circadian rhythm of the body and causes changes in metabolites and can lead to bigger problems such as obesity, cancer, and renal disease. Thank you.